interesting problem that's actually not very unusual, which is to say, imagine I am sitting here and I've got a couple different circuits that's sitting in some legacy component. And I'd like to be able to move this into more modern structures, say an FPGA. And at this point, I need to really be able to take a look at it and go, okay, what do I do with this? And what I'm realizing is, and this is true typically, that there's a whole bunch of these things just sitting out there that all the documentation's long gone because the people who built this was probably like 20 years ago or more, and nobody has any idea what's going on. So you're like, well, I've got this thing that's made up of some components and I've got some connections here, and I need to figure out how to, one, figure out what was actually there, and then do some analysis and going, okay, well, what is this circuit? Because then if I say I'm going to put this on an FPGA or some other related structure, I need to at least know what I'm repeating. And so sometimes you kind of get surprised. You're like, well, I wonder what's here. Well, what you see on this board is you see where you've got your typical ground and VDD line, which is very typical. And then you would have two 7400 chips. These are NAND gates. There's 4 NAND gates in there where you actually have your inputs and output, 2 inputs and output. And then you've got a ground supply and a VDD supply on pin 7 and 14. Now, if you're not quite sure, you always get the one pin here, which tells you where, and right to the one side of it is where pin 1 is. So same thing here. And so what you realize is that you go, well, I could just kind of stitch my way through this and see what the circuit is. It turns out there's 6 gates used here. And so of these 6 gates, you have to figure out, all right, what do I have? And I have 6 gates. I have some intermediate points, point C, I have X1, X2, and I can build from there. Well, what does it look like? Well, one of the interesting things, if I look at A, I've got double connection here to an output, and then double connection to an output, double connection, and that gets in the circuit. That's 3 inverters in a row. Kind of interesting, actually. It's almost like it's trying to make a delay, and you go, well, that's A, and it's 3 inverters here. And then I also have that the A and that inverse, that whatever that term is, which I'm going to call C for the moment. These both feed into NAND gates that have this terminal B. B basically in this circuit is going to turn out to look like a selection. It's going to be like, am I turning it on? Am I not turning it on? But then the rest of this is like, well, what else is this circuit? Because then I'm going to take a NAND and that's my output. And you're like, that's an interesting circuit. And in fact, if I look at it from the C points, from C point here, B and A, I could actually write out what the output is, and knowing that the C is 3 inverters. And you might be tempted to just say it's A bar, which is true for part of the timing, but not all of the timing. So this is very much a conversation of, well, what does the timing do? Part of that's going to be important is to go, well, what happens in terms of these elements? And having 3 NAND gates effectively acting like an inverter in this configuration gives me 3 unit delays. We're going to say about 10 nanoseconds for delay is what we're going to kind of build from, and we're going to build a first order model. It would depend a lot on the capacitance of the board, depends on a bunch of things, depends on the chips you got. Let's just run with this number because it's a pretty realistic number given a lot of the type of chips you would see for these kind of TTL chips. So, all right, so we have the output equals to these components. And an interesting thing that you notice is if B equals 0, the steady state value of this is going to be that the output is going to be basically 0. Because you put zeros in both of these elements, you work your way through, and you basically get 0. Cool. Interesting thing happens if B is equal to 1, then your output gives you this kind of function of A plus C. Now wait a minute, C is the inverse of A. That would tell me that, well, A plus A inverse should always give me 1. Thinking, well, that's kind of interesting, but not quite everything. And if A goes from 0 to 1, C starts at 1 to 0, so I still get 1 throughout. But if A goes from 1 to 0, C then goes from 0 to 1, and I get out going to 0. And then returns back to 1. And it's an interesting thing then when you say, what does the timing diagram look like for this? And so you get two parts. You get A going up and down, and B going up and then down. Well, when B is down, one of the things you notice here is that the output pretty much stays down to 0 pretty much the whole time. There's really not much that you're going to expect otherwise here. And that's kind of cool. That kind of makes everything feel fairly straightforward when you're putting this together. Okay, that's nice. So I'm going to get pretty much a 0 there, and it's off. But interestingly enough, then when I have B on at 1, a couple of things happen. And this is where all the interesting dynamics happen. One, I actually get an interesting start at the beginning here on that edge, which is kind of fun on the X2 terminal here. I get a small jump here. But the more interesting part is that I get a spot where X1 and X2 are both high. And that gives me something that starts to push down towards ground, down to 0 for a time. And it gives me a pulse, and it's a pulse of a certain width. What's the width of the pulse? 3 unit delays. It's basically 30 nanoseconds in that space. So it works out really well, and it's kind of interesting to see that. Now, if you didn't notice this part of the timing diagram, you would just think that this is just going to be 1 all the way through, and you just completely miss the point. But the whole point of this is to say when I hit the value A, and it's going to go down, it's going to create a pulse. Now, it doesn't matter how long A is down, but every time A goes down, I would see this dynamic. So it's really interesting of the kinds of things you see in the dynamics. It's really interesting that you can actually look at an older circuit or any circuit that's built and figure it out and kind of systematically work your way through these kinds of problems.